So we're going to start off with this warm-up. There are 6 integrals here that we know how to do most of them. In fact, we can do all but one of them. So I would suggest that you try to do as many of these as you can, and then check your work after a moment. So I'm going to have the answers pop up here in 5, 4, 3, 2, pause the video, 1, ta-da! And here are the answers to the 5 that we already know how to do. The first 2, well, the first one is straightforward, just memorize. Then we've got the other one on the top right is U sub. We've got integration by parts. We've got integration by parts twice, so tabular method is better here. And then we've got another U sub down here on the bottom right. So the only one we don't know how to do is this one, which looks benign enough, but we actually can't do this one until we learn a trig identity. Okay, so let's go back in time to pre-calculus, and well, actually, let's not learn that trig identity yet. I forgot. More to come. Stay tuned. But the one on the right, notice is the bottom right here, this cosine of x, sine squared of x. We can deal with a lot of different integrals that look a lot like that, as long as we have one of the either cosine or sine raised to the first power. Then we can let u equal the other one. So for example, here we're going to let u equal not the sine to the 7th of x, but just sine of x. And over here we're going to let u equal not cosine to the 88th of x, but just cosine of x. So basically this is going to boil down to integrating u to the 7th du, and this is going to boil down to integrating u to the 88th du, and neither one of those is very hard. They're just inverse power rules. Of course, you're going to have to worry about whether you have a positive or a negative based on your u substitution. I'll let you work on those on your own. So what happens then if we have something that's got a sine squared, right? Just a sine squared, like we had up here. Or perhaps just a cosine squared. And those are where we're going to need those trig identities. So if you recall back in pre-calculus days, some double angle identities. Our most useful double angle identity is the cosine double angle identity, because we can take this cosine squared of x minus sine squared of x and rewrite it using Pythagorean IDs. For example, if we want to eliminate the cosine, we can replace cosine with, well, cosine squared, with 1 minus sine squared, right? So that means that cosine of 2x is the same thing as 1 minus 2 times the sine squared of x. And that's another identity that we learned last year in pre-cal. So if we take this cosine of 2x equals 1 minus 2 sine squared of x and solve for sine squared of x, we can get, let's see, it'll be 1 minus the cosine of 2x divided by 2. And since those are the same thing, we can deal with either one of those. And the one on the right is easy to integrate. We can do the same thing with cosine. So instead of replacing cosine squared, we'll replace sine squared. Whoops. Sine squared of x is the same thing as 1 minus cosine squared of x. So that we're going to get 2 cosine squared of x minus 1 equals cosine of 2x. And we'll get a very similar identity. This time we're going to get 1 plus cosine squared of x equals 1 plus cosine of 2x all over 2. Okay? So those are identities that will help us reduce the power of squared sines and cosines. So we'll have 1 minus the cosine of 2x here, all over 2, and 1 plus, this, it's still cosine, cosine of 2x over 2. Okay? So we're going to need these if all of our exponents are even. So for example, we can rewrite sine squared of x as 1 minus cosine of 2x over 2. And we can factor out that 1/2. Integrating the 1 turns into x. And then we have to integrate, minus. We have to integrate cosine of 2x. Well, cosine integrates to negative sine, right? No. Cosine integrates to positive sine because the derivative of sine is positive cosine. Trying to get that to go away. There we go. So the derivative of negative sine will be negative cosine. So we want that sine to stay the same. The SIGN sign. Anyway, we have to undo the chain rule. So we've got a 1/2 there. And that's our final answer. You could pull out another 1/2 and get 1/4 2x minus sine of 2x. If that makes you happy, sure, go for it. Either way. Now, if we change the argument to 3x, then same sort of idea happens. Just remember that whatever this is, we have to double it to get to this. So this is a cosine, so we'll have 1 plus, because our identity has a plus there, cosine of not 3x, but 6x. And everything else stays pretty much the same. I'll factor out the 1/2, and I'll get x plus 1/6 the sine of 6x plus c. So nothing too fancy going on there. We just need to know a trig identity in order to integrate them. Where it gets kind of fancy is when we have something bigger than 2 as our exponent. So if we have 4 as our exponent, you might say, well, so what? Well, let's take a look at this. We don't have a power reducing identity to the 4th power, but we can write this as cosine squared of 2x, and then I can square that. So inside the parentheses, we've got cosine squared of 2x, and then we're going to square that. But instead of writing cosine squared of 2x, I'm going to rewrite that as 1 plus cosine of 4x over 2. All right. Well, that means that I can square this out. The 1/2 becomes a 1/4, and I get 1 plus 2 cosine of 4x plus cosine squared of 4x. Because we're squaring a binomial, we have to have all 3 of those terms. And we can integrate 1, we can integrate 2 cosine 4x, and we can integrate cosine squared of 4x as long as we apply the identity one more time. So my preference is to do all of the expanding it out before doing any of the integration. So cosine squared of 4x is 1 plus cosine of 8x. Remember, we have to double that argument when we perform this identity, all over 2. And now each one of these pieces is integratable. I'll rewrite it one more time because we've got a 1 plus a 1/2 is 3/2. And we've got 2 cosine of 4x. And we've got 1/2 cosine of 8x. If you feel like distributing that 1/4 out front into everything, you can. If you feel like factoring out a 1/2 so there aren't any fractions here, that's fine too. The world is your oyster. But I'm going to leave it as is. And let's see, the 3/2 turns into 3/2 x. The 2 is going to get divided by a 4. 2 over 4 is 1/2. Sine of 4x. And then this 1/2 is going to be divided by 8, so we're going to get 1 over 16 sine of 8x. And all of that is plus c because that is our indefinite integral. So that is an acceptable final answer for this particular integral. All right, so what happens if we try to do this to the 6th power? And you might start getting a little bit sad if you see where this is going, because we know how to deal with sine squared, but we actually have to cube that. So we actually have to say, well, that's this whole thing cubed. That whole thing can be reduced to 1 minus the cosine of double the argument of x over 3 to get 2x over 3. And so the cubing the 1/2 turns into a 1/8. And then we have to cube this binomial. Pascal's triangle, anyone? 1 minus 3 cosine of 2x over 3 plus 3 times the cosine squared of 2x over 3 minus cosine cubed of 2x over 3. I'm going to put a little sad face here and say, that's pretty rough. But that's how we could do it. Okay, we actually haven't figured out how to deal with this cosine cubed yet. But perhaps we can revisit that in a future example. I don't really feel like finishing this problem because these things get so out of hand so fast. So I'll leave this as saying, well, this is how we would do it. And if I were to personally put this on a test, I would probably just say, what would be the first step? So we wouldn't get lost in the weeds because this is a fairly involved process. So in your homework, yeah, definitely go through the process of doing this, but just be more familiar with the process. And if you get lost along the way, it's okay because these things are pretty gnarly.